Hi everyone, I'm Julianne from the Edmonton Public Library, and welcome to Mad Science. Today, we're going to learn about chemistry by trying out some simple chemical reactions that you can make with ingredients that you find in your own home. We'll complete an engineering experiment by building bridges out of spaghetti and marshmallows. And finally, we'll learn a bit about physics when we participate in an egg drop. Before we begin, I wanted to remind everyone to be kind with each other in the chat section. I'll be doing a bit of time traveling and will be moderating the program. So if you have any questions or comments as we go along, please feel free to enter them in the chat bar. I'm going to begin today's program with a quick poll. What is your favorite type of science? Is it biology, the study of living things? Or chemistry, the study of the properties and composition of substances and the changes they undergo? Or is it physics, the study of motion, energy, and forces? There are lots of different branches of science, and we're going to explore some of these today. As we work through the experiments, we'll be using the scientific method. The basic steps of the scientific method are 1, to make an observation that describes a problem or question. 2, to create a hypothesis or a proposed explanation made on the basis of limited evidence, or quite simply, what you think will happen. And 3, we'll test our hypotheses. Next, we'll draw conclusions or state what we've learned. I'm going to ask you what your hypotheses are for each experiment. And now we'll move along to our first experiment, balloon magic. Welcome back, everyone. Our first activity today is called balloon magic. We're going to learn how to blow up a balloon in an unconventional way with chemistry. We'll be combining baking soda and vinegar together in a type of chemical reaction called an acid-base or neutralization reaction in order to create water, salt, and gas, specifically carbon dioxide. Before we begin, let's define some terms. Acids and bases. So almost all liquids are either acids or bases to some degree. And whether a liquid is an acid or a base depends on the type of ions it contains. Ions are tiny atoms or molecules that have either a positive or negative electrical charge. Acids contain hydrogen ions, which have a positive charge, and bases contain hydroxide ions, which have a negative charge. Some acids can be found in the food that we eat. So these include acetic acid, which is found in vinegar, lactic acid in milk, and citric acid, which is found in lemons. Acids often have a sour taste and are corrosive, which means that they can cause metals to rust. Our bodies use stomach acid to help break down the food that we eat. Bases, on the other hand, can also be found in some foods and medicines. They often feel slippery when you touch them, and they have a bitter taste. Baking soda is an example of a base, as is milk of magnesia, which our parents might give us if we have a sick tummy. When acids and bases are combined, they produce water in compounds called salts. Some acid-base reactions also produce gases, and this is why baking soda is useful in baking pastries and cakes. When it's combined with an acid like lemon juice or sour cream in a dough mixture, it releases gases that make the dough rise. So, what ratio of baking soda to vinegar is best for blowing up balloons? Well, now that we know a bit more about acids and bases, let me introduce you to the acids and bases that we'll be using for today's experiments. In the red corner, we have vinegar, which contains acetic acid. And in the blue corner, we have baking soda, which contains sodium bicarbonate, a base. When we combine the two ingredients together, we'll produce water, salt, or sodium acetate, and gas, specifically carbon dioxide. The gas is what we're especially interested in because the gas that's released in our chemical reaction is what's going to inflate our balloons. And the question that I have for our first experiment is, what ratio of baking soda to vinegar is best for blowing up balloons? In front of me, I have 5 bottles. Each bottle contains 100 milliliters of vinegar. There are balloons on top of each bottle, and the balloons have a different amount of baking soda loaded into them. So for our first bottle, I've added 1.25 milliliters of baking soda. Our second bottle has 2.5 milliliters. Our third bottle has 3.75 milliliters. Our fourth bottle has 5 milliliters of baking soda. And our sixth bottle has 6.25 milliliters of baking soda. We're going to experiment to see which balloon blows up the biggest, and therefore which experiment creates the most gas. I'm going to take off my glasses and put on my safety goggles for this experiment, just in case any of the vinegar or baking soda spray out of my balloon. So we'll make some space here. Let's begin with our smallest amount of baking soda, 1.25 milliliters of baking soda into 100 milliliters of vinegar. And let's see what happens. So I've added the baking soda, and I can see that a chemical reaction is happening. There's lots of bubbles in my vinegar, which means that gas is being produced. And as you can see, my balloon has blown up a little bit, but it's not too big. So we'll try our next bottle. So in this balloon, I've added 2.5 milliliters of baking soda. We're going to tip up our balloon and add that baking soda into our vinegar. We have a chemical reaction again. I'm just going to swirl it around a bit. And let's see if we produce more gas with this particular example. And I can see it's bubbling nicely. And when I compare my two balloons, I definitely have produced more gas in this second chemical reaction. So we're definitely moving in the right direction. My third bottle has 3.75 milliliters of baking soda that we're going to add to our 100 milliliters of vinegar. And let's see what happens. Does anyone have any predictions as we move along about which bottle is going to have the biggest balloon and which reaction will be best? So we'll try here. And there goes my baking soda. It's bubbling even higher, this chemical reaction. And I'll swirl it around to make sure we have all of the ingredients mixed here. So here we go. We definitely have small and then a bit bigger and bigger still. Okay. Our fourth bottle, again, has 100 milliliters of vinegar and 5 milliliters now of baking soda. And what I'm wondering is if there's going to be a maximum amount of gas that we can produce. Eventually, as I keep increasing the amounts of baking soda that I'm adding, I'm going to maximize or saturate the vinegar below. So there may be a time when our balloons stay the same. So we'll see if that happens. So 5 milliliters of baking soda. Here we go. And I'll swirl that around a little bit more. That is an unexpected result. I'm not sure what happened, or whether perhaps... Oh, here we go. So sometimes when you're doing an experiment, the unexpected happens and you have to troubleshoot a little bit. It looks like some of the baking soda that I had placed in my balloon got stuck and didn't come out. I was wondering why my balloon was smaller. But now, all of my baking soda seems to have been added in, and the balloons are just about the same size. Okay, we have one more bottle to go. So our last bottle has 6.25 milliliters of baking soda in our balloon and 100 milliliters of vinegar. And let's see what happens. Who thinks it's going to be the biggest balloon? And who thinks the balloons will be the same size? Let's check our hypothesis. Whoa! And this is the biggest reaction yet. I can actually feel some of the water moving into the balloon. And I'm just going to hold it on because I want to make sure it doesn't spill out. So this definitely was a really reactive experiment. The bubbles happened very, very quickly. Now, when I look into the bottom, I can see that the reaction is still taking place. It's still bubbling. And when I compare the size of the balloons, 6.25 milliliters is indeed the biggest balloon that we have. So we know that when it comes to the ratio of baking soda to vinegar, using 6.25 milliliters of baking soda to 100 milliliters of vinegar gives us the biggest reaction and the largest amount of gas. Now I'm going to take off my safety goggles, put on my glasses so I can see you better. So now that we have that ratio, we are actually going to move forward to our next experiment. We are going to make baking soda and vinegar volcanoes. Hi everyone, welcome back. So now that we have the perfect recipe for a great bubbly chemical reaction, we're going to use it to make some amazingly bubbly lava for our homemade volcanoes. So here's how to make a volcano using a big piece of paper and a small bottle. The first thing that you're going to want to do is to place your bottle upside down in the center of a great big piece of Bristol board or thick paper. You'll want to make a circle around your bottle top, a little bit bigger than the bottle neck itself. Then you'll lay your bottle flat against the paper and draw a big circle around it. Again, bigger than the bottle itself, but nice and round. The next step is to grab a pair of scissors and cut out the shape of the largest circle. Then you'll want to cut a hole in the middle of that big circle and cut out the circle at the center of your volcano. The next step is to decorate your piece of paper with some paint or crayons to make it look like a volcano. And sometimes that paint can take a long time to dry, so I've pre-painted my volcano paper for today. Then you'll want to overlap the sides of your circle to make a cone shape and tape the pieces of the cone together. So that will make your beautiful volcano. I have a pre-made volcano that I'm going to use for the purposes of our experiment. So I'll place it right here. Okay. Now our next step is to put the ingredients in our bottle to make a chemical reaction. So based on our last experiment, we discovered that 6.25 milliliters of baking soda was the perfect amount to mix with 100 milliliters of vinegar. So I've already added it to my bottle. I'm going to then, here we go, to the 6.25 milliliters of baking soda, I'm going to add 30 milliliters of water. So that will turn my base into a base solution. But I still have the same amount of that basic base of baking soda for my chemical reaction. My next step is to add about 15 milliliters of soap. And what the soap will do in our chemical reaction is trap some of that gas to make a nice frothy foam. So just like in a real volcano, the molten rock will sometimes trap some of the gases that are escaping the volcano, and that can make the lava that comes from a volcano sort of foamy and filled with gas. So, there we go. So I've added my soap now to my water and my baking soda. The next step is to add some food coloring to the mixture because we're going to want our lava to be beautiful and red. So I'm going to add 1, 2, 3 drops of food coloring. And we'll shake it around. So far what we have is just a nice red liquid. I'm going to trade my glasses for my safety goggles for the chemical reaction that we're going to make, just to keep my eyes safe in case any of the baking soda or vinegar splashes up. And now I'm going to take my bottle filled with red liquid and I'm going to put it in the very center of my volcano, like that. Okay. Our next step to make the chemical reaction happen is we're going to want to add our vinegar to our base mixture. I'm going to use a funnel and pour it from a little bit of a height. Now, if you're doing this experiment at home, you'll see that I have a table that's covered in a bit of paper. This experiment can be a little bit messy. So at home, you might want to do this experiment in a sink, or if you have a tray or a basin, just to keep the mess to a minimum at home. But for the purposes of our experiment today, we're going to let the lava flow onto the table and we'll clean up the mess later. So here we are. I'm going to add the vinegar and let's see what happens. Oh my goodness. Here we are. So we have a beautiful, foaming, red, kind of pink volcano. You can see that the lava is oozing out over the sides. The soap that we added to the mixture is trapping our bubbles, and it looks just like a real volcano. So fabulous job, everyone. Our next experiment is going to be something entirely different. We're going to move away from chemistry and we're going to take some time to build some bridges out of spaghetti and marshmallows. So we'll see you in a second. Welcome back, everyone. So as you can see, our next activity is all about bridges. We're going to use spaghetti and mini marshmallows to build bridges together, and then we'll test them to see how much weight they can hold. If you don't have spaghetti and marshmallows at home to build along with me, no worries. You can use lots of different types of materials to build bridges. You could use popsicle sticks and Play-Doh, toothpicks and gummy candies. Basically, you just need something straight and something gooey to hold those straight pieces together. Now, there are lots of different types of bridges in the world, but many bridges use one shape in particular to give them strength. Can anyone guess what that shape is? Let's do a poll. Do you think it's a circle, a square, a triangle, or an octagon? If you said triangle, you're right. Triangles are used in bridges because they can evenly distribute weight without changing their proportions. And when multiple triangles are joined together in a bridge, they're called trusses. So I'm going to do a bit of an example. I'm going to build a square shape and a triangle shape, but first I'm going to move this to the side. Okay, so if you are building alongside me at home, you can feel free to build a square shape and a triangle shape as well. Here we go. Whoop. Now, here is my, oh dear, it's already falling apart. Oh no. Here's my square shape. And as you can see, by the trouble that I've been having with it already, it's quite wobbly. If I apply a force to the top of this shape, what happens is it's going to want to flatten either to the left side or to the right side. So it's not very strong and stable. Now, as an example, if I build a triangle shape, and I can actually modify, here we go, my square shape, I'll reuse some of the pieces. Here we go. If I build a triangle shape, like this, and apply force, it's a little sturdier. If I apply force to the top, what's going to happen when I press is eventually it'll fall apart on the bottom, but it's much sturdier than the square. It doesn't want to bend to the left or to the right. What's happening is the weight that's on top is being distributed down the sides where it's compressing, and along the bottom where it's facing tension, it's pulling apart, which is why ultimately it will break at the bottom part. Okay, so I will move these pieces back to the side here. So as we've discussed, compression and tension are two of the forces that happen when we make a bridge and we place it across two braces like this. So using this piece of foam as an example, if I apply a force or a load to this foam, you can see that it wants to bend. And when it bends, that's because the top of it is being pushed together in the force of compression. And the bottom is moving apart with the force of tension. So it's shortening at the top and my foam is lengthening at the bottom, and that causes the foam to sag. So those same forces will act upon the bridges that we construct. However, the materials that we're using aren't as flexible as this foam. So we know that our bridges will eventually break. The top part of our bridges, because they're compressing, will buckle. And the bottom sides of our bridges, because they're facing tension, will snap. So I have made some different bridges at home. And what we're going to do next is we're going to test the strength of each type of bridge. The first bridge I made is a Warren truss bridge. Warren truss bridges are made by joining equilateral triangles, or triangles whose three sides are the same length. Combining the triangles together applies compression and tension in different places. On this bridge, the beams being compressed are painted red, and the beams that are experiencing tension are painted blue. My second bridge is a Howe truss bridge. This bridge uses diagonal beams that slope upward to meet at the center of the bridge, where they meet in an upright isosceles triangle. Isosceles triangles have two sides that are the same length and a third side of a different length. Like the Warren truss bridge, the beams that are being compressed are painted red, and the beams that are experiencing tension are painted blue. My third bridge is completely made up of triangular pyramids. There's not a real world example of this bridge. I made it up entirely on my own. And I'm not sure with my third bridge which beams are doing what. But like all of the bridges, I know that in all likelihood, the top of my bridge will be being compressed and the bottom of my bridge will be experiencing tension. Now, I'll show you my third bridge in a moment, but let's do a quick poll. Which bridge do you think will be the strongest? Is it the Warren truss bridge with its equilateral triangles? Or is it the Howe truss bridge with its isosceles triangle and its diagonal beams? Or do you think that the bridge that I made up completely on my own will be the strongest? So we'll take a poll. You can let me know which you think will work the best, and we'll go ahead and we'll begin testing our bridges. So the first bridge that we're going to test is our Warren truss bridge. So I'm going to move this piece to the side, and I am going to place my Warren truss bridge. Oh, I already have a piece falling off. I'm going to place it on top of our two supports. And then once it's there, one at a time, I'm going to add a car to the bridge. And we'll keep track of how many cars the bridge can support. before it collapses, and they will collapse, hopefully spectacularly. So, carefully, carefully. Here we go. All right. We have our Warren Truss Bridge. On the count of 3, I'm going to stop supporting it in the middle, and I'm going to begin adding cars, and we'll see how many we can add before it eventually collapses. So, 1, 2, 3. Here's our first car. Our second car. Oh my goodness. 2 cars. So our Warren Truss Bridge, while kind of strong, only held 2 cars before it collapsed. And it collapsed in just the way that we described above. So you can see that it sags out. The beams on the bottom of the bridge separated, and the beams on the top of the bridge squished together. Okay, I am going to move my destroyed bridge off to the side. We'll pick up our cars. And let's see now how many cars our Howe Truss Bridge will support. So if you guess that the Howe Truss Bridge will be stronger, let's see how that works out. I wonder if it will. It does have a few more support beams holding it together. So let's see if I can pick it up without breaking it. Here we go. Okay. So far, so good. This does seem to be perhaps a little bit more stable. Okay. So on the count of 3, I will stop supporting it in the center, and we'll begin adding our cars. 1, 2, 3. Here goes our first car. 2, 3. Oh, okay. So our bridge didn't completely collapse. We did have a bit of a failure in the bottom, so our 3 cars fell off. I wonder if we can redo this one. Let's see how many cars it actually takes for it to completely fall apart. So I'm going to use these pieces. I'll stick it back together a little bit more. And it is entirely possible that it will fail in the same way. But so far, this does seem to be the stronger bridge. Okay, so we'll count down again. I've got my cars out of the way. We'll see if the same thing happens. 1, 2, 3. So 1 car, 2 cars. And the same thing happened. The cars actually fell out the back. It looks like the same side of my bridge over on my side here is the part that seems to be coming apart, but the top of the bridge is holding together. So I know with this bridge, it definitely is stronger than my first bridge. And I hadn't tested them before, so that's really interesting to know. But where this bridge comes short is on the bottom. So where the forces of tension are pulling the spaghetti from the marshmallow is where this bridge ultimately fails. But it could successfully hold 3 cars before it collapsed. Now I'm going to move this bridge over to the side. And then I will bring out the bridge that I made all by myself, which is completely made of triangular pyramids. Now, I thought because triangles, are a strong shape, that perhaps those pyramids would work in my favor. But like I said, no one in the real world has ever made this type of bridge to hold cars. So let's see how it works. Okay. And here we go. So it's a very modern looking bridge and a very unique looking bridge. And because, and a bridge that's already falling apart. Uh-oh. Because I don't know all of the science behind this bridge, I'm not sure which beams are facing compression and which beams are facing tension, other than the fact that likely at the top of my bridge, as we discussed before, things are compressing, and the bottom of my bridge is going to be facing that force of tension. But let's see how many cars my bridge can support. Ready? 1, 2, 3. 1, 2, 3. Oh, that wasn't too bad. My bridge did fail in the same way that the Warren Truss Bridge failed. So it definitely didn't hold up as much to those forces of compression in the top. And of course, the forces of tension made it sag, and it's still collapsing. So I think if we had to choose a winner for the strongest bridge, when we compare the Warren Truss Bridge, the Howe Truss Bridge, and my own personal bridge, I think that our Howe Truss Bridge is the winner in being the strongest bridge. So this is going to lead into our very last activity for the day. We are going to experiment a little bit with an egg drop. So I'm going to take a moment to tidy up, and we'll see you in a second. Hi everyone, welcome back to our fourth and final experiment from today's class. So I am here in my laboratory in the Imagine Room at the Shelley Milner Children's Library, and we are going to drop some eggs. So let's talk a little bit first about the science behind the egg drop and what happens when we drop an egg from a high place. The eggs I'm using today, just so everyone knows in advance, are hard-boiled eggs, so we don't have to worry too much about making a mess. They will be my supper this evening. So when we drop an egg from a high place, there are a couple of forces acting on that egg. We have the force of gravity that's pushing down on the egg, but we also have the force that is being exerted by my egg drop machine, which is pushing the egg up and holding it in place. This egg has a lot of potential energy, meaning if I pull this lever and the egg begins to fall, it can travel at quite a high velocity onto the ground. Now, when I pull the lever and the egg begins to fall, it's still being acted on by the force of gravity, but there isn't an equal force pushing up on the egg, so it will fall. And the potential energy that the egg has right now will transform into kinetic energy. When the egg reaches the floor, it is suddenly back in an environment where it's being acted on by a force that's pushing up on it by the floor. So at that point, the kinetic energy of my egg transforms back into potential energy, but the force of the floor pushing up on my egg and the velocity of the egg moving down is what will cause our egg to break. So what we are going to do in an egg drop is try to create a cradle to protect our egg. There are two factors that we should consider when we're making the cradle to protect our egg. So the first is to maximize the drag on our egg so that we can slow down the egg as it falls. The second factor is to try to minimize the impact, to help absorb the energy that the egg experiences upon impact so that it doesn't break the egg. So I've constructed 3 different cradles that we can test today using materials that I found around my home. I have 3 cups of different sizes, a small cup, a medium cup, and a large cup. I have some bubble wrap. I found some styrofoam and some bits of wire. So let me show you my very first cradle that I've constructed. Here we go. Using my smaller cup. Now, in order to maximize drag, I've added a parachute made out of a coffee filter, and I've added some wings made out of foam. Now, the great thing about the small cup is I know that it's light, so it won't speed up too much as the egg falls. So let's go ahead and I'll take my egg from my egg drop machine and I'll place it inside the cradle. And the question of the day is, will this cradle be successful in protecting my egg? So I'll put it on top of my egg drop machine. And on the count of 3, I'm going to pull the lever, which will send the egg falling. So 3, 2, 1. Ooh, let's see what happened to our egg. Oh, and I see that I do have a small crack on the bottom of my egg. So my very first cup wasn't quite absorbent enough to counter the shock, to counter the energy that my egg experienced as it hit the floor. So my first cup wasn't quite protective enough. We'll move on now to a new egg for my dinner. I'm going to have at least 1 egg for supper. Whoops, here we go. We'll reset my machine. And so this egg cup I made with a little bit of a sturdier parachute made out of craft foam. A paper cup that was a little bit bigger, and I have something that I'm going to place inside of it. Because my cup is a bit larger, I can actually place some tissue paper inside to see if that will help to protect my egg. In fact, I'm going to try wrapping my egg completely in the tissue paper and putting the squishy part down. Okay, so again, what I'm hoping is that my craft foam parachute will create enough drag to slow down my egg, and that the tissue paper I've used inside the cradle will actually help to absorb some of the shock when the egg hits the ground. So we'll put cup number 2 on my egg drop machine, and we'll do a countdown again. 3, 2, 1. That didn't sound quite as bad as when the first egg landed, but my egg cup did land this part down. So let's take a peek and see if the egg inside is broken or if it's okay. And as you can see, in this case, my egg did not break. It's actually perfect. So I know that it isn't because of the drag that was created by my parachute, because it didn't quite fly properly. So I think what worked in this experiment was the tissue paper cushioning the egg from the blow. The carpet likely also helps to absorb some of the shock from my egg. Now, we're going to use the same egg, actually, since it's not broken, in our third egg drop. And this time I've used an even larger cup. Okay, so I'm going to reset my egg machine here. And this is my third cradle that I've created. So this cradle is even bigger, this cup is even bigger still than the last cup that we used. So I can put a little bit more material inside of it. And this time what I've decided to use is a little bit of bubble wrap that I found at home. For the parachute, I decided that I would use an even bigger piece of bubble wrap that I also had laying around, and I'm hoping this time that will actually help my egg cup, my cradle, land with the bottom down. We'll see if it works. So again, I'm going to take my egg and I'm going to wrap it, again this time in bubble wrap that I find is even cushier than the tissue paper that we were using before. And I'm going to put it inside my bigger cup, and we'll place it on top of my egg drop machine. And I can see already that my parachute is ready to go. I'm hoping this time it lands the right way around. So 3, 2, 1. Oh my gosh, it landed upside down again. I think possibly the distance between my egg drop machine and the floor isn't quite enough for my parachutes to pick up the draft of the air. But let's look inside again and see how this time the bubble wrap did in the fall. Did it manage to absorb the energy from the egg hitting the floor. And again, I have a perfect egg for my supper. It did not break. So in this case, both of the medium and the larger sized cup provided enough room for me to put packing, either tissue paper or bubble wrap, around my egg to keep it safe. If we were using eggs that were dropping from a higher height, that might not be the case. But in science, sometimes you never know how an experiment is going to turn out. And so this brings us to the end of our program for today. I hope that you all had a lot of fun. If you have any questions, or if you wanted to tell me what your favorite experiment was today, please let me know in the chat bar. And if you'd like to participate in more virtual programs for Summer Reading Club, please visit us at www.epl.ca/SummerStarts. We'll see you next time.